So I think we can start. It's our great pleasure to have Professor Jacqueline Hewitt with us today, giving the Faculty of Sciences colloquium. Professor Hewitt started her career by getting a bachelor's degree in economics, actually, in 1980, and thankfully for the field of astronomy, she realized the error of her ways, and in graduate school embarked on a very long and successful career in astronomy and radio astronomy specifically. She has a long history with MIT. She did her graduate degree at MIT, getting a PhD in physics, then did postdocs at the MIT Haystack Observatory and also Princeton for 1 year before joining them as faculty in 1989. Since 2000, she was full professor of physics at MIT. Since 2017, she has a prestigious named chair position, the Julius A. Stratton Professor of Physics position. And since 2002, she was serving as the director of the famous Kavli Institute for Astrophysics and Space Research at MIT. And she just stepped down 2 months ago, so she held this position for 17 years, and she says she's very excited to let go of the reins for a little bit, and she's here on a well-deserved sabbatical. For her research, as a graduate student, Professor Hewitt became involved already with radio telescopes, which would stay with her throughout her career. She was analyzing images from the very long baseline interferometer that she took as a graduate student, and she noticed a curious ring, and this ring was later identified to be the very first Einstein ring, gravitational lensed ring ever discovered in the lensing system MG1131. She's pioneered throughout her career techniques in radio astronomy, interferometry, image processing, and with a focus on astrophysics and cosmology. She has recently been very interested in the observational signatures for the first stars, the epoch of reionization, which we'll hear about today, as well as the detection of transient astronomical radio sources. She's won numerous awards. I just took a brief list, but it's not the complete list because I don't want to take up too much of your time. She has the Harold Egerton Award for work on gravitational lenses, the David and Lucille Packard Foundation, which is a very prestigious, generous award in the US, the Henry Booker Prize for the National Union of Radio Science, Maria Goptert Mayer Award for radio astronomy, the Sloan Fellowship, which is a really, really prestigious, generous US award, the Annie Jump Cannon Award in astronomy, and she was the Time magazine's 25 most influential people in space in 2012. She has shaped the direction of science throughout her career. She was part of her research and also as chair on many panels. She was the chair in the program prioritization panel on particle astrophysics and gravitation in the US 2010 Decadal Survey. She was the chair of the Radio Astronomy Commission of the International Union of Radio Science, chair of the Committee of the Review of Progress towards the Decadal Survey Vision in the New Worlds Survey. She was also instrumental in the development of many telescopes, which we take for granted, without which we wouldn't have such scientific developments. And MIT has a tradition of not only supporting the research, but also developing the science, getting their hands dirty, and developing the telescopes and engineering. Through her guidance, MIT has been a founding member of the MWA radio array, which is one of these first generation arrays that is looking to image, that is looking to statistically map out the first billion years of our universe in the radio signal. And now there's she is one of the founding members of the hydrogen epoch of ionization arrays, which is the next generation array, which can revolutionize our understanding of the very first galaxies and stars that appeared in our universe. She also, as part of this, managed to convince the Moore Foundation to donate $6 million to the Hera effort, which was a whopping 1/3 or more at the time of the total budget of the telescope. So without her, who knows if we would have the successful telescope that is being built today, probably not. And the last time I visited MIT, actually, she took me on a tour of the Transiting Exoplanet Survey satellite, the TESS satellite, which was just launched last year, whose goal is to detect exoplanets through as they pass over stars, and you detect the drop in the intensity, and it's going to do a survey that's going to give us a whopping 200,000 potentially such systems that could revolutionize our study of transiting exoplanets. But as part of this, I was struck how proud and excited she was as she was showing us all of these lovely instruments that were being developed, and who knows how many telescopes would not be as good or not even exist were it not for Professor Hewitt. So welcome, please, and we'll hear more.
Well, thank you, Andre. That was a very nice introduction. I really appreciate it. And I have to say, I'm so glad not to be director anymore. I'm on sabbatical, and this is a wonderful way to start my sabbatical, is to be invited by you to come interact with the scientists here and to give this talk. So thank you very much. It's a real honor to be here. And I do plan to tell you about the work we're doing at MIT in looking for the first stars. And it's actually very closely related to work that's being done here. I've known Andre for quite a while now, and we've frequently interacted. He does more of the theoretical end of things, and as he pointed out, I'm an experimentalist and an observer, so I really enjoy building instruments to measure these exciting things. So what I plan to tell you is let me just say, I understand this is not just an astrophysics audience, so I'm planning to put this whole thing into the context of the cosmology theories we have now and the work we're doing, and also talk a little bit about the theoretical simulations that Andre and others have worked on that are trying to model the processes of the formations of the first stars. And in particular, I want to talk about this radio probe of neutral hydrogen that is my specialty, and I think is one of the several different ways that we're going to use to explore this part of the universe. I'd like to tell you the results of the first generation of those instruments we have built, one of which was the MWA, just bring you up to speed on where we stand with those, and then I'd like to focus on Hera, which I think of as a second generation instrument, and we're nowhere as near being done with our Hera work, so don't expect any final results today from Hera, but I'd like to give you a progress report and where that work stands. Okay, so here goes. Here's the universe in one slide, a cartoon. And the astrophysicists in the audience are very familiar with this, but for the others in the audience, this is a plot which shows us here on the right and the beginning of the universe here on the left. And the time goes from left to right. The vertical axis here is a measure of the radius of the universe. So the universe expands very quickly, we believe, at the beginning, and then expands more slowly until the present day. And I'm going to be using the word redshift repeatedly in this talk. I just do that automatically. Redshift refers to the amount to which the light from a distant source is redshifted because of its recession velocity. And because of the way the universe expands, it scales with distance, it scales with look-back time, and all of us in this field use the word redshift to mean distance or look-back time. So you will hear that. The redshifts we are interested in are from here to here, from a redshift of about 7 to a redshift of 1100. Okay, so let me just turn this a little bit. And so redshift 1100 is, redshift 1100 is the time at which the microwave background was released from the plasma at the time. It was when matter and radiation separated. The universe became transparent, and we could see this wall of plasma at a few 100,000 years after the Big Bang. Redshift 7 is another big observational landmark. It is where the highest distance about to which we see normal objects like galaxies and quasars. We actually see them to about 10 now. And people use various words to describe this important part in the history of the universe. That doesn't show up too well, but in this region here, people refer to that as the Dark Ages. It's a time in the universe before there were any stars. It was very dark. There was matter, dark energy, and neutral hydrogen, but the neutral hydrogen was cold and just glowed from its own temperature, which actually was very cold. And then we consider the next part of the history of the universe here to be the cosmic dawn, when the stars first turned on. And we're starting to be able to study that now. We're going to be talking to that now. And finally, the epoch of reionization, which we often talk about, is the time at which the neutral hydrogen, which is an important constituent of the universe, particularly before the first stars, was actually ionized by the first stars and became ionized again. It was originally ionized back here. It recombined to form neutral hydrogen, and then there was a big change in the universe right around redshift 7 or so when the intergalactic medium ionized again. So these three sort of times in this part of the universe are what we're going to be studying right now, in particular the cosmic dawn and the epoch of reionization. So let me go on and review a little bit what we know, the context of the cosmological model that we're doing all this work in. This is the microwave background. I think this is a famous picture that even people outside of astrophysics have seen a lot. It's a measure of the surface of last scattering that, because of the universe has expanded, is now seen in the microwave radiation. And it is our best information we have about the universe as a whole. And if we take the Fourier transform of that sky and look at the angular composition, fit spherical harmonics to it, this is what we get. And the data here are the little red dots and the red lines here. And the truly remarkable thing is that we can just make some very simple assumptions about the basic properties of the universe. And I list them here, and I think a lot of them are sort of intuitive, that there's one set of laws of physics that describes everything in the universe. General relativity describes the geometry and the way mass and gravity behave. The universe is the same everywhere. It's expanding. There's certain constituents that we believe that we allow for in the universe. Space is flat or nearly flat. There are initial conditions that are natural in terms of an inflational theory. And the topology of space is trivial, meaning that it's just connected in simple ways. We can't just hop over to another galaxy far away there is no, hyperspace or anything like that, like in science fiction. And if we just make those simple assumptions, it turns out we can define 6 parameters, okay? And it doesn't really, I'm not going to worry too much about what they are in detail, but it's convenient to define 6 parameters of this model, and we can tune the models of that parameter, tune the parameters of that model, and when we do so, we get this blue line here, which remarkably describes all the information in the microwave background, or most of it anyway. And that is truly an amazing result, I think. And it makes us think that we actually understand quite a bit how the universe works. We understand why it expands the way it does, how distance and time are related. And so I can use a redshift, and from the redshift infer a distance or a time. And so this allows me to do the kinds of experiments that I'm going to be describing for the next of the talk. So just to put those 6 parameters, though, into something a little bit more intuitive, you can take those 6 parameters and from those derive other quantities, and those I think are a little bit more intuitive. And as you've probably heard, one of the things we learn is that only a small fraction of the universe actually has normal matter, about 30%, the kind of matter that that interacts gravitationally the way we think. And the rest of it is this form of dark energy, which is a very different kind of substance that has a energy density that doesn't change as the universe expands. In normal matter, the energy density goes down. And that's necessary to describe the data that we saw in the microwave background. And that's a really astounding result, I think, and won the Nobel Prize, of course. And also, if we convert those 6 parameters into some other quantities, we learn that the age of the universe is 13.8 billion years, which is a nice thing to know. And it's the way we've parameterized the universe, the assumptions we've made, means there is this sort of beginning that we can identify. And by measuring the rates of expansion and all that, we get the 13.8 billion years. We're also able to measure the amplitude of the initial fluctuations, and that's going to provide initial conditions for the rest of the work I'm describing. We can measure the shape of the spatial fluctuations, and again, that provides initial conditions for the rest of the work we want to do. And finally, we can work out what the redshift of reionization must have been, just from the number of electrons that are between us and the microwave background, and we can tell how many electrons there are between us and the microwave background by the patterns that I showed you. And it comes out to be a redshift of 7.7, nearly redshift 8, which in fact is in this range. It's right about here on this picture. And in fact, well, this picture is sort of drawn to reflect that, but it all hangs together. We expect the redshift of reionization to be around a redshift 8 from other reasons. Okay, so that's the cosmological context of this work. It's the work we've done. And it's really an amazing work that has been done in measuring these parameters so precisely and describing those microwave observations so well. But I would say that there's still a lot to be understood. I mean, we've got really precise measurements, but there's really a lot we don't yet understand. For example, we don't really know, and experiments are continuing so that we can try to understand these things. For one of the things, we have no idea what this dark energy is, and I would claim we don't even know what experiments to do at this point to figure out what it is. We don't know what the dark matter is. Of that 30% of matter which behaves normally, we've only identified about 5% of it in stars and galaxies. All the experiments that except for maybe some exceptions which are under debate, have not managed to turn up what this dark matter is. We don't really know much about these initial conditions, where there are searches. I've tried to list some of the experiments that are going on to address some of these questions. There are searches for non-Gaussianity. There are things that could go beyond this sort of very vanilla model that I've described, like could there be this deviation from flatness, which we've assumed. There's some hints and other measurements that the Hubble constant we measure from the microwave background is not coming out the same as the Hubble constant, the rate of expansion that we measure with other techniques. So there are things beyond this sort of vanilla model that we're starting to explore as the data get better. We need to test whether this assumption of general relativity is correct. The model we've set up doesn't even address what might have happened before this so-called t equals 0. It's probably not that simple. This model that we've set up doesn't even allow for the possibility that there might be more than one observable region of space, so that there might be more than one possible universe. And a big question is, why is there this direction of time? So I hope I've given you a sense that even though we've done this amazing measurement of figuring out, be able to predict these fluctuations in microwave background with great precision, there's still a lot of understanding left. And so the last question I'd like to throw out there, which is the one we're addressing, is how do you go from this very sort of uniform cosmological soup to the structures we see today, to stars, galaxies, planets, and eventually even life? And so how does that actually work? And that's what we'd like to address by studying this region here, where we go from this microwave background, smooth background, to a universe in which we have stars, galaxies, and planets and people. So let me start by telling you what we know, at least give you some examples of the things we know from this time, this period of time in the universe. And I'm going to start with ones which aren't in the radio area because I want to go into that in some depth later. Okay, so here's some information we get from taking infrared measurements of the sky. When you look at the sky, there are literally billions and billions of dots in the sky, points of light that are stars and galaxies. And at this point, to the best of my knowledge, we know that exactly 4 of those dots actually are quasars from a redshift of between 6 and 7. And remember, the microwave background measurements tell us that the redshift of reionization is about 7.7. So this is right in the range of the reionization era that we are considering. And it's the reason we're able to tell that 4 of these spots in the sky are different from all the other spots in the sky is from this spectrum of their emission, and this is mostly in the infrared band here. So this is a spectrum of one of the objects, and it's just the energy as a function of wavelength. And what's characteristic about these objects in the reionization era is there's this big absorption to one side of the hydrogen line, Lyman alpha. And that's because as we go back farther in time, when we get back to this era before reionization, there's a lot of neutral hydrogen all of a sudden, and that absorbs this emission. Things which are closer to us than this region of reionization do not have that kind of absorption. And so the way we identify objects that are in the reionization era is by taking broadband photometric measurements. We put filters in front of our telescopes, and these plots down here are plots of the response of the different filters, how much energy they emit as a function of frequency. And this big absorption feature here appears as what we call a dropout. I mean, there's just no spot at this point here because the light has all been observed. So by examining literally, tens of thousands of the objects or more and looking for these abrupt changes in brightness of certain filters, astronomers are able to identify objects that are in the epoch of reionization. And so this is information we have about that period. Now, if I go to the next slide, this is work done by one of my colleagues at MIT, which I chose this one. I believe Andre has also done similar work on other objects. But here's again the same spectrum of this quasar. And now the idea is that we're going to measure how much has been absorbed here, and by measuring that absorption, infer how much neutral hydrogen is at that redshift, and therefore whether or not the universe has ionized at that point. Because when it ionizes, it goes from being neutral to being ionized, and it won't absorb anymore. And the difficult part of this sort of measurement is to know what the quasar looked like before it was observed, because not all quasars are the same. So a lot of the analysis in doing this kind of work is figuring out how do we extend the spectrum of this quasar as to what it looked like before the hydrogen absorbed it, and then measure the absorption. And here, this on the right is a plot of different possible neutral fractions of the hydrogen gas and the likelihood that that value is correct based on the data. And so the answer is that the neutral fraction of hydrogen at this redshift of this object, which is 7.5, is around 0.5 or so. And so this is supporting evidence, actually, that the redshift of reionization is around 7.7. We have, these four quasars. The others look kind of like this, where their spectra are absorbed here to such an extent that we infer that the hydrogen is about half ionized. So that's very interesting. It completely different line of reasoning and evidence that we are seeing the epoch of reionization around a redshift of 7 point something. Okay, here's another example of the sort of data we have from this epoch of reionization. This is a whole collection of spectra like I just showed you, but at lower redshifts, ranging from about redshift, around up to about 6, I'm not sure, 4 to 6. And this is the absorption feature that I pointed out before, and you can see as you go to higher and higher redshift, it's more redshifted. I mean, that's the point. And what's interesting here is as we look at a relatively low redshift quasar and look at the absorbing gas between us and them, which is down at these wavelengths here, you can see that there are places where the light gets through. You can see these emission. And that's because the gas is ionized here. It's in the regions where the gas is ionized, there is not as much absorption. And so here we know that reionization is finished. But when we go to an object which is at a higher redshift, we start seeing this area here in its spectrum where there's almost perfect absorption. So this is another line of evidence that we're at the epoch of reionization, because this absorption would only happen if the gas is neutral, okay? And so this is similar evidence as before, and it's telling us from these spectra here that the reionization was basically finished by the time we were at about a redshift of 6. If the gas were still neutral at about a redshift of 6, these would be completely absorbed. So here's another piece of evidence that the epoch of reionization occurred higher than a redshift of 6, probably around 7. So that's from optical spectra. And here's a little bit of a more recent result. Again, I'm giving you examples of the kind of information we have from this era. This is plots for a lot of different quasars of redshift from about 4 to 6.5, okay, getting on the edge of the epoch of reionization. And here on the vertical axis is a measurement of the optical depth to scattering. And that is basically a measure of how many electrons there are between us and the quasar. And as you get deeper into the quasars get farther and far away, this optical depth goes up, indicating that we are seeing more absorption. But what I wanted to point out here in this work is that there's a great deal of scatter in this, okay? And that's because these different quasars that we're observing in different directions on the sky. So this absorption pattern that we're seeing is very much direction dependent, which is evidence telling us that the reionization process, when it occurs, is not uniform around the universe. It's not occurring at exactly the same place all around the sky. Some places it happens later, some places it happens earlier. We call this patchy reionization. And that actually is a sort of clue as to what's causing the reionization. It can't be something that's very uniformly distributed, or it could be. I mean, the evidence isn't very strong yet, but it's a hint that's what's causing this reionization may be something like a smaller number of brighter objects rather than a large number of fainter objects, which would give a more uniform ionization. And so these are the sorts of data that we are using to try to understand this process of how the first stars formed and first lit up the universe. So now, those are examples that are not out of my field of radio astronomy. So now I'd like to switch now to what I want to talk about the rest of this talk, which is the radio astronomy techniques that we are using, which complement these optical and infrared techniques. And so the answer, what we're going to do, I want to talk to you about using this neutral hydrogen gas itself and observing it directly through the way it emits and absorbs radio waves. And like I said, this complements other probes, galaxies and quasars, which we study by the light that they emit at optical infrared. So at our redshifts now, at our times, this neutral hydrogen tends to be found inside galaxies. There's a lot of neutral hydrogen inside galaxies, but outside the galaxies, the gas is ionized. Okay, and here's a picture, one of my favorite examples actually here, of how much you can learn about an astronomical system by mapping out the neutral hydrogen structures in it. On the left is a picture of a nearby small group of galaxies in optical light, and it's a reverse image, so things that are bright are dark. Okay, so this is a Leo triplet of galaxies, and just an optical picture, you just see the usual stars. But here's what it looks like in radio emission, and you can actually see that these galaxies are interacting dynamically. There's hydrogen gas that's throughout the whole system, and you can measure its velocities, and you can learn a lot about the system by looking at this sort of extended gas tracer that exists in regions where the stars do not exist. And so you can actually look at how these galaxies are related and how they interact. So that's a nearby example of the 21 centimeter line, and I'll get back to that in a minute. But here's a little cartoon of what we can actually do with that in a cosmological context of the universe as a whole. This hydrogen gas exists everywhere. In the present day, it's ionized between galaxies, but present inside galaxies. But when you get out to the epoch of reionization, okay, I should say this picture is just a schematic of the universe with us at the center, and then redshift infinity at the beginning of time, if we look back around the edge. And the epoch of reionization is the same range of redshifts we've been talking about, which is here in blue. So in principle, if we can map that hydrogen from these sets of redshifts, we'll be mapping the entire structures which are inside the epoch of reionization with a 21 centimeter line. For contrast, this purple spot here, which goes out to about a redshift of 2, is a type of volume that we're able to really uniformly map with large galaxy surveys at this time. Okay, we have galaxy surveys which go deeper, but they tend to be sort of narrow in angle. We can't do the whole sky with those. So the feeling is that we should be able to take this hydrogen structure and really get a large-scale, broad view of what's going on at high redshifts. And in fact, in principle, there's no reason we can't extend it all the way to the redshift of 1100. because the hydrogen actually gas is neutral all the way back during that time. It only becomes ionized at redshift 7.7 or whatever it is. And so this is actually potentially a huge probe, a very valuable probe of the entire of structure formation in the universe as a whole. So that's why there's so much interest in building these large radio arrays, to be able to explore this neutral hydrogen at throughout the whole universe. So just for the people who aren't astronomers in the audience, it's just some basic physics that goes into this. It's the hydrogen atom, which is about as simple as you can get, and the hydrogen atom has energy levels, which are, with spin-orbit coupling, are split into different levels. But once you include the spin of the nucleus of the hydrogen atom, you get the fine structure splitting between levels, and as the atom makes transitions between those states, it either absorbs or emits light with a frequency of 1420 megahertz. That is a 21 centimeter wavelength, so this is the famous 21 centimeter line of neutral hydrogen, and that's basically what we plan to observe. Now at MIT, this is sort of a standard oral exam question. I don't know if you guys have, I'm sure Andre loves to ask this one, but you can convert, from basic physics, you can go from this hydrogen atom and do a radiative transfer calculation as to how bright the radio glow should be, the spectral line you would measure from a cloud of hydrogen gas at redshift 7 of temperature, which has a spin temperature that refers to how these levels are populated, compared to the microwave background temperature for a given baryon density in the universe, and we know this from, that's one of the parameters we measured with a microwave background. Given a density enhancement delta at that location and a neutral fraction x at that location, you can take all that and do a fairly simple calculation, and you work out that you should see temperature from the place you're observing of 27 millikelvin, and then it has a dependence on all those quantities that's shown in this equation. So measuring that temperature actually tells you what the neutral fraction is, what the density enhancement is, and what the spin temperature is, which is extremely important things that, for astrophysicists at least, to measure about what's going on around the epoch of reionization and before. So we can use these temperature measurements to learn those things. Furthermore, this line is optically thin, which means we can see through the gas all the way to high redshift. And so we can measure these quantities at all these different redshifts and recover a lot of information about the universe. So that's a basic idea. And okay, with this idea, we now want to connect to the models we have of the formation of structure in the universe, which so much work has been done on that here. And the way we do that, computers have changed our life in many ways, and one of those is it makes possible to do extremely detailed simulations of the universe. And so we simulate the emergence of this structure on computers, basically by taking the laws of physics and taking a large collection of particles and gas and allowing those, the laws of physics to evolve on the computer. I've shown one example here, which is the Illustris simulation that one of my colleagues at MIT is heavily involved in. And what's shown here on this picture is the results of the simulation after you take the initial conditions that we learned about when we measured the microwave background, put all the physics into computer code and run it forward and see what you get at t equals 0. It's amazing, actually, these things. Here's a dark matter distribution, okay, which traces the structure. This panel here is the gas distribution. The gas is modeled as well as the dark matter. And from all the information that is kept as you run these models forward, things like temperature and entropy, et cetera, velocities of the different gas can all be recovered from these simulations and compared to experiment. So that's our goal, is to make a similar picture only with data from the 21 centimeter line of hydrogen of temperature and velocity and density and compare it to these simulations. Okay, so this is really a sort of a different way of doing science, is comparing big data simulations to big data we get from our instruments and finding ways to compare them. So these simulations, there isn't a simulation that has modeled everything. We do not even now have computers that can model every aspect of the physics that we're doing. And so the simulations that different groups work on will tend to pick out different physics to emphasize and depending on what we want to measure. And so now I'd actually like to switch to some of the work which has been done. I'm sorry, I switched our topic. So let me, we'll in a minute switch to some of the work that's been done here. But first let me just say something about the overall signal of the universe. If we take measurements of the sky and average them, we can measure an average temperature of the hydrogen that we detect all the way around the sky. And that's something we've referred to as a global signal. And before going on to the simulations, I wanted to say a few words about that. And there are 3 plots here of theoretical predictions of what that global signal should look like. On the plot are different temperatures. On the right-hand side here is a high redshift, so in the distant past. On the left here is the present at redshift 0. And so what these plots show are these quantities and how they evolve as a function of look-back time or redshift. The top panel is temperature. This line here is the temperature of the microwave background, okay? And that, on this kind of, the way this plot is drawn, is just a line that as the universe expands, the microwave background cools, and the temperature goes down linearly on this particular plot. Okay, this line here is the temperature of the gas in the universe, and because the gas is a non-relativistic gas, it cools differently from the microwave background. It cools more quickly, and the temperature of the gas becomes different from the temperature of the microwave background. If you could pull that picture out again, please. So I could see the equation at the bottom. Yeah, thank you. That's this here. This is the difference between the spin temp. This is the temperature of the microwave background. This plot here is the temperature of the spins of the hydrogen, so how the hydrogen levels are populated. And for reasons, and that evolves with time. When the universe is very hot and dense, the spin temperature is the same as the gas temperature. As the universe expands, the spins tend to connect back to the microwave background temperature. And then there's a process which happens as when stars form, where photons, Lyman alpha photons, fill the volume. And because of the presence of those photons, the spin temperature of the hydrogen is able to thermalize back to the temperature of the gas. And so the temperature of the gas, temperature of the hydrogen atoms goes back to the temperature of the gas. And so we get this complicated behavior of the different temperatures, and because of this equation here, where the observable depends on the difference between the spin temperature and the microwave background temperature, you get this behavior down here. So what gives us the radio signal is the difference between this temperature and this temperature. And so you expect to see the radio signal from these different redshifts. First, it's a negative, a depression in the temperature, absorption against the microwave background. Then it goes to 0. Then it's an absorption again against the microwave background. And then as the universe heats up, it's a temperature and emission against the microwave background. Okay? So it's a very distinctive pattern that we expect as a function of looking back in time, which means because of the redshift looking at lower frequencies of the hydrogen, we expect to see absorption, a cold line, absorption again, and then emission. And I just wanted to now make a connection to experiment. I think the astrophysicists here are all familiar with this result, but there was recently a report of a detection of that absorption signal that I just described in the global signal. So this is believe it or not, this is the experiment. You can't really tell the scale here, but it's about this big in the Western Australian desert in Western Australia because there's not much radio interference. And this is what is measured by this antenna. You put a receiver on the end of that antenna and measure the spectrum, and you just see this very smooth spectrum. And that's a spectrum mostly of the radio emission of our galaxy, okay? But then if you subtract a smooth spectrum from those data, which is what you expect from our galaxy, you're left with this signal here, which looks kind of funny. On the other hand, if you subtract the smooth spectrum plus an absorption feature, you're left with what just looks like noise. And this is a very oversimplified presentation of that experimental result. The people who did this experiment, I have a great deal of respect for. I'm sure they did it very carefully and worried about the difficulties of this measurement. They have checked the results over and over again, and they believe that they really are seeing this absorption signal in the radio spectrum, the globally averaged radio spectrum, as they detect it with this small antenna. And that's truly a remarkable result if it holds up. It is a detection of this predicted absorption of the microwave background by the cold hydrogen gas, in this case at a redshift of 17, okay? And this could be a signal of the formation of the very first stars. The very first stars would create a bath of Lyman alpha photons, which would cause this feature here to appear. We are still having a lot of debate about whether this is actually the correct interpretation of that line, but if it is, and this is the first detection of the sort of cosmological signal of the first stars. Okay, another thing that this measurement of this signal does, it tells us potentially, it tells us that there, okay, if the cosmological interpretation is correct, it tells us there were some first stars there were some Lyman alpha photons. It tells us the gas is cold, otherwise we wouldn't see an absorption against the microwave background. And it tells us also to some extent, how much gas must be there. And so now the question is, what does this say about whether or not we can detect other things? And of course, the presence of that signal, if it's right, gives us more confidence that we're going to be able to detect other aspects of the signal. So let me move on now, how am I doing on time? Is there a clock? To these other aspects of the signal. 15:44. How much time do I have until 4 o'clock? Sorry, is there a clock in here? Okay, I'm sorry. I wasn't expecting to have the computer at this angle, so it's a little hard to see. Okay. So the sorts of, we would also like to see the fluctuations. The stars as they form should produce ionization patches in the neutral hydrogen. And so now I'm showing you some simulations that were done here by Andre's group, which shows different redshifts at redshift 7, redshift 7.7, redshift 6.7. These are a little bit old. I don't know if you have them tuned to the latest information. But the point is, the star formation occurs during the epoch of reionization. You see very patchy patches of neutral hydrogen, and we should be able to see those patches if we actually map the sky. So let's, and the way we do this statistically, okay, here's just one redshift, one slice of the universe at a certain distance, and we take the Fourier transform again, and this time in 3 dimensions, and we expect that the cosmological signal is going to be spherically symmetric, right? The fluctuations we see in the neutral hydrogen. And so we just average them in spheres, and then we get a measure of the power spectrum, the Fourier transform, just as a function of radius in the Fourier transform space. We call that as a function of k. And so what we are looking for are fluctuations in our data which match the sort of signal that's predicted by the theories of structure formation. So that's the goal of the radio experiments that I'm about to describe now. So let me skip some of that since, there we go. And so to measure those fluctuations in the hydrogen brightness temperature, if you work out what the redshift implies at redshift 7 for the radiation that we'll be receiving, it's going to be redshifted, the 21 centimeter line will be redshifted to 50 megahertz to 250 megahertz. So that's the area in which we need to look to be able to find those redshifted signals. And this, goes back, people have been working at those low frequencies since the 1930s when radio astronomy started. So why are we just doing this now? And in fact, I'm always sort of amused. I know Craig Hogan, this was his PhD thesis in 1979, was actually pointing out that this would be a good measurement to do to detect the formation of the first stars or structures. And the reason it's not been done, it's a very difficult measurement to do. For example, the 50 to 250 megahertz is right around where the radio and television bands are. And so there's a lot of man-made emission at those frequencies. And here are just plots that we actually took when we were looking for somewhere in Australia to do these measurements. This is the radio sky spectrum, so power is a function of frequency in Sydney, Australia. In Narrabri, which is a place in Australia where there's a radio observatory, actually, still not so good, it's on the east coast. And this is in Western Australia, where there's nothing except a few people and some sheep. And so, obviously, we can't do this sort of measurement like anywhere in the United States, I don't think. And so one of the real challenges of doing this measurement is radio frequency interference. Another challenge is there are a lot of things in the sky that are very bright, and here, just for example, is a map of our galaxy at radio wavelengths, and that's 10 to the 5 times brighter than the signals we're trying to see. So that's an issue. This is a map done with the Westerbork radio telescope in the Netherlands, which just is a map of the sky showing sources. There are point sources of radio throughout the sky due to quasars and galaxies, which are between us and the cosmological signal we want to see. And they're also much brighter. And so these are real challenges of doing low-frequency radio astronomy. And we really only are able to, for a lot of reasons I don't have really time to go into, we are able to address those challenges by being able to do very high-speed computation digital signal processing, which is expensive. We could have done these experiments 20 years ago, but only if we had like a Department of Defense budget to make them actually fit within the sorts of funding agency capability. We are now, because of improved signal processing computers, we can actually build the radio arrays that can do this, and we can actually solve some of the data analysis problems. So now let me switch to the actual experiments that had been done. I promised you a summary of the first generation experiments. And here they are. I think I'd like to identify 5 experiments that were done in the first generation. This is each one of these pictures shows one element of a radio array. These 4 pictures, one element of a radio array. And so imagine these things that I'm showing you, but duplicated 100 or 200 times to make a radio array. And probably the one that looks most familiar is a giant meter wave radio telescope in India, which is sort of a familiar radio dish. These others are all sort of funny shaped, twisted pieces of metal, which turn out to be good shapes, good designs for being able to test these low frequency radio emission. So it's actually been a lot of fun trying to design antennas which actually do this. They're all sort of variations on dipoles. This 5th experiment here, MIT EOR, Meteor we called it, was never actually a detection experiment, but did a lot of a small array that we used to do some important technology development. And even though it was very small, it turned out we learned quite a bit from it. These other ones actually, we did some measurements of the cosmology signal we were looking for. And here's where the different antennas experiments were located. Let's see. That's where the Murchison Wildfield Array is, the one I worked on. We went to Western Australia to do it for the reasons I showed you when I showed you the plots of the radio interference. The paper, the Precision Array for Probing the Epoch of Reionization, which Berkeley was the PI institution for that. They chose to go to South Africa, again, because there's not much radio emission. What I have shown here, this is a map of emission at 131 megahertz, just done by a satellite that was studying the sun or something, but just shows you where the world is bright at low frequency radio emission. It's not bright in Western Australia or South Africa. This is the Indian one, the giant meter wave radio telescope. It's got moderately bad radio interference. This is the MIT experiment we did. We just drove up to Maine, where there's a relatively radio quiet, and set up some antennas and worked there. And this is where the LOFAR antenna is. This is right in the middle of very bad radio environment. I think they deserve actually a lot of credit for having developed techniques for dealing with a bad radio environment. Okay. So just to remind you, what these experiments are looking for is these experiments map the sky, and as a function of frequency, which is a function of distance because of the redshift. So we have 2 dimensions on the sky, the depth due to redshift, Fourier transform, average in spheres, and we are looking for these distinctive power spectra that are predicted by a theory that people like Andre do. And let me just, now I have to get a little bit into the weeds here, and I apologize for that, but I think it's important for understanding some aspects of the measurement. We don't just have the cosmology signal in the sky. We also have point sources, resolved and unresolved, but that's sort of a detail, the synchrotron emission from our galaxy, and then noise. And one of the things that makes this sort of difficult is the point sources and the galactic synchrotron all have a spectrum which is very flat, okay? And so I've drawn that, actually Josh Dillon drew this, drawn this so as constant lines in this direction. So on the sky, our galaxy and foreground sources have a pattern on the sky, but in the z direction, the frequency direction, the redshift direction, they're just constant brightness. And that's different from the cosmological signal. The cosmological signal has a pattern this way, but it also has a pattern this way. It's not flat in the z direction. And it's that difference that we are using to separate the cosmology signal from the foregrounds, from the galaxies and the sources. And so let me show you another picture of Fourier space. Before I showed you the power spectrum just as a function of k, the radial dimension of Fourier space. But that doesn't work anymore when you have the foregrounds, because the foregrounds are not spherically symmetric. The foregrounds have cylindrical symmetry, right? They're symmetric on the sky, and then they're different in the z direction. So I'm plotting here cylindrical space, where this is the Fourier direction along the line of sight. So if I take the Fourier transform in the z direction, frequency direction in the data, I get this. This is the Fourier transform in the direction on the sky, and then I average an annuli on the sky, and I end up with this cylindrical space rather than spherical space of Fourier transform. Now, because the sources have a flat spectrum, you would expect, when you take this Fourier transform, the foreground sources, our galaxy and point sources, will all land here. There'll be a lot of power here and zero power here. And that would be good, because that means all the foregrounds are all limited to this part of Fourier space, and just the cosmological signal is in this part of Fourier space. But however, because of the way our instruments perform, the foregrounds actually get spread out into a triangle here. It just has to do with the fact about how the instrument behaves differently at different frequencies. And we've always called that the wedge. Okay, this has become kind of a dictionary in our lexicon of doing these experiments. This is the wedge. But then there's the EOR window, which is the part of Fourier space, cylindrical Fourier space, where the foregrounds do not exist, because they have a smooth spectrum. And so this should be, if we Fourier transform and average in the way I just described, the foreground should all appear here, and just our beautiful cosmology signal should appear here, and all should be good. So that's what we've been trying to do with the first generation experiments. Take these images of the sky at different frequencies, which forms a three-dimensional space, Fourier transform, average in such a way that we have a cylindrical Fourier space, and then isolate the signal in this part of space, which should be just the cosmology. So that's what we've done. Does that make sense? Sort of. Okay. And this is the result. I want to show you the result from one of these experiments, which is the one I worked on. I just thought I'd choose the one I worked on. And so this is actually data. This is not theory anymore. And this is the brightness in this cylindrical Fourier space of the data we took with a Murchison wide field array. And sure, and this line here shows where the wedge should be according to the design of our instrument. And look at that, it's actually pretty amazing. All this flux is down here. And up here is what we attribute to cosmology and errors in our instrument, all right? Because we haven't really gotten this working yet. And so from the flux that's here, we can turn this into, we can just only use the data that's in this area, now go back into spherical coordinates. And then we present our measured power spectrum here. And interestingly, we have detections here and here. This is our measured power spectrum, the points with error bars. And if the error bars go all the way down to 0, it means that we don't have a detection. That's just a limit, okay? But we actually have detections here and here. And let me draw your attention to this feature here. That is not cosmology. That is a reflection on one of our cables. You cannot perfectly impedance match all your cables. And as we learned, whenever you have a reflection in your system, you end up with a band of power here in this Fourier space, which is not cosmology, but which is a systematic error that you can't get rid of very easily. And so that's actually what limited our ability to detect the cosmology in the first generation of experiments, is a lot of these reflections. So let me make a long story short and just show you the summary of all the first generation experiments of the results. This is as a function of redshift. Remember, we expect the echo of reionization to be in this range here. This is one of Andre's predictions here of where our signal should be. And here is where we we either detected something which is a systematic error, or we detected nothing. We view these as limits on the power spectrum. The power spectrum measurement is here or below. And so that's where we are with the first generation instruments. We have not detected this, but we've done a great deal to improve the sensitivity of the instruments to get closer and closer to being able to make a detection. For those of you, if I'd been giving this talk 3 years ago, I would have showed this plot. I just need to say this. These points here, they have been retracted. These points have been retracted by the collaboration that made those points because there were some issues in their data analysis. So this is now the current version of this plot. Unfortunately, some of the reported upper limits have been retracted, and so we are still about an order of magnitude away in power spectrum amplitude, the square root of, 2 orders in the power spectrum magnitude to having a sensitivity. We learned a lot from these experiments, and now we're moving on to the next generation where we're increasing the sensitivity, so we hope to be able to actually make a detection. So let me now talk about Hira, which is a second generation instrument that we're working on, and let's see. I'm not going to talk about SKA1 low, which I know is something many people here are involved in. So let me just say briefly, the motivations for Hira are to detect this power spectrum, as I said. We want to do other aspects of epoch of reionization research, for which you need a more sensitive instrument. We also want to go to lower frequencies where we can detect the actual heating of the intergalactic medium by the first stars before there were enough stars to ionize. And we're also putting in a lot of design changes, for example, being more careful about the reflections on cables, just to incorporate lessons that we learned from the first generation. So the group here has done simulations that show how the universe, how the heating as well as the ionization happened. And so I don't have time to go into this in detail, but the point is we have some very interesting prediction, thanks to the group here and elsewhere, of how the intergalactic medium actually heated. And this is at even higher redshifts, like redshift 20 or so, before, when the very first stars were just getting going. And we want to check those predictions. So here is an artist rendering of Hera. And it's going to, we actually have the funding, happy to report. So it's going to consist of 320 elements that are arranged in this core, and then an additional 30 elements, which are outliers, sort of, that we need just to get longer baselines, so for certain aspects of the measurements. And the reason these are the choices we made in the design. We need more collecting area. We think that's very important to get the sensitivity, and the best way to get that at low cost is just a fixed dish in the ground. It's expensive to build them so that they can point, so it's just a fixed dish. It's a transit instrument. We've chosen the focal length and other dimensions, actually, of the whole system, so there are no reflections at the length scales that would block the EOR window where we want to do the measurement. We have a smaller field of view. It turns out that's easier to calibrate. And if you notice, this looks very different from other radio telescopes that you've probably seen, like the VLA or even SKA low, in that it's a very regular array of dishes. And the reason for that is it's much easier. We feel we can do a more precise calibration of a radio array, which is very redundant, where there are many pairs, baseline pairs in the array which measure the same thing. And therefore you can calibrate because you have many measurements of the same thing. And you don't actually have to know what the sky is. You can solve for the sky at the same time. So with almost no information about the sky, you can completely solve for the performance of your array. In principle, okay? We have to see if it actually works. Now, a very redundant array is not very good for imaging properties, and so that's why we put in these, we've fractured our crystal here, so it's not completely redundant. And we did a lot of simulations, and with 3 different sort of crystals there, we maintain enough redundancy that we can still calibrate the array, but we also recover some imaging properties. Okay, and so we've also, this is a schematic of the sky. Because our dishes are fixed in the ground, we're going to just be observing this declination strip here. We can't, just a range of declinations that are accessible to our fixed dishes. So this shows the schematic of our Hera stripe on the sky, and these are simulations of what the EOR picture should look like if we should, someday when we map this. And we've chosen this strip so it's away from the galactic plane. That's the galactic plane. We want to look at the cold cosmology sky. And here's a comparison that we did at the time of proposing this instrument of the Hera to SKA low, which has a very different design. And it's about a factor of 10 difference in collecting area. These are the 3 first-generation instruments. Let's just compare Hera and SKA low. And you can see there's about a factor of 10 difference in collecting area, which is also about a factor of 10 difference in price. Hera is about a $20 million instrument, and I think SKA low is around 200 million or so. And here are predicted signal to noise of the true instruments. And if you work only in the EOR window, which is what we mean by foreground avoidance, you only take data in here because the foregrounds aren't there, then Hera should actually outperform the SKA by quite a bit, okay? And that's because we've chosen the baselines to be all in the EOR window. We've put the antennas close together. On the other hand, if you actually can subtract the foregrounds and remove them and use the entire Fourier space, then the performance is about comparable, because the SKA low has a lot more of its information coming from within that wedge where all the foregrounds are. And if you can subtract the foregrounds, then you can use all that information. If you can't subtract the foregrounds, you can't use the information. Hera can do a better job of detecting. And here's a picture of the array as it exists as of a few months ago. I really love this picture. It reminds me of a Magritte painting. So let me just give you a status of where we are with Hera. We have been operating the array with high band feeds. These feeds work from 100 to 200 megahertz. We've been operating for a season with those with 50 antennas. Let me skip this because in the interest of time. We are now working on extending the redshift band. We have been operating in this green region. This is redshift. These are predictions of what we expect to see. These are the EOR signals. This is the sensitivity of Hera. We've been working in this range. We're now working to extend the redshift, to extend the performance of the instrument to higher redshifts. And we're doing this by building a different kind of feed to hang at the top of the antenna. We've explored 3 different designs for a broadband feed. For the past year, we've been building prototypes. We've been going into the workshop and building prototypes and hanging them on a test dish we have in West Virginia and measuring various properties. And at the end of the day, we've decided to go with this design here. This is a so-called Vivaldi feed, which we are now going to replace the high band feeds and hang them on the antennas, so we brought in the frequency response. And we actually have been working hard also to build antennas. This is the status of the array as of a month ago. There are 270 dishes built. If you can see these yellow squares, that's where we have the broadband feeds, and the triangles are where we've put electronics on them. So this is moving ahead quite rapidly. That's what it looks like. There are a bunch of dishes out there that don't yet have feeds on them, but they're coming. And here are some of the new broadband feeds actually hanging on top of the array, and this sort of dramatic moment when the sun was lighting them up so you could see them. So we now have 24 of them on the instrument now, but only 12 of them have receivers. We are now operating with 12 broadband feeds. This is a map we made just recently when we had 6 broadband feeds operating. 6 antennas is not very many, but here's Fornax-A, here's another bright source, here's the plane of the galaxy. So we're seeing what we should be seeing with 6 antennas. So far that works. So that's where we are in this line of research. So I just wanted to close with a status of Hera, which is our experiment. We have a lot of data taken with this high band system from 100 to 200 megahertz. The power spectrum analysis is underway. We hope in a few months to have some results on that. We're right now starting to take data with a broadband system, and as we're taking data, we're continually building, we're just adding broadband feeds, keep building antennas. And we expect to have 350 antennas operating by the end of 2020. And so then we'll have a full experiment running. And finally, just to summarize the status of our 20-centimeter cosmology, we have this amazing global signal result, if it's right, and we have to wait to see if this gets confirmed or whether other experiments see it. The first generation experiments are essentially complete. We have learned a lot about how to measure power spectrum. We've been pushing down the limits on the power spectrum. And we're now all working on these second generation experiments, which in principle should be able to detect the power spectrum and allow us to look at the evolution of the power spectrum. So that is a work in progress, and I hope to be able to come back in a few years and give a talk about detections. So that's all I had to say, and I will leave this beautiful photograph up for inspiration, and let's welcome some questions.
What is your opinion about the origins of the 21 centimeter axis?
The 21 centimeter, were the edges result, or?
What do you think about the origins of the 21 centimeter absorption axis?
You mean the experiment, whether it's right? Yeah. I actually, if you'd asked me that a year ago, I would have said, no way, can't be right. But we've all been talking about, what types of systematics could cause that to occur. And just to give you an example, it turns out if you have a ground plane that's about this big, it'll produce lines in exactly that part of the spectrum. So I thought for sure it's their ground plane which is resonating. That's what they're seeing. They just doubled the size of the ground plane, and the resonance should have moved, and it didn't. So, and they've been changing the shape of the ground plane, and it does not go away. Every systematic effect that we think might be causing this, it has not, we check for that, they check for that systematic effect, and it's not. So I'm beginning to actually think that's probably correct. But do you mean from a theoretical point of view? Not the experiment, I'm sorry, okay.
I mean, there are models which explain this,
right.
attribute this effect to a diameter.
Right, okay, so I didn't have time to go into a lot of detail, but the absorption signal is stronger than it's supposed to be, according to the theories. It's also broader than it's supposed to be. So it could either be that to get a deeper absorption line, you either have more absorption or more emission to begin with. And so maybe there's more than the microwave background in the background that's producing the background. And so it could be a population of radio sources that are raising the background emission. Or it could be that the gas is a lot colder than we believe, and I don't know. We're having a lot of discussion about that. I mean, Andre knows a lot. It could be a population of galaxies that we don't know about yet, which existed for a while and created the ultraviolet the Lyman alpha photons that you need to do the Lyman alpha coupling to cool the gas.
And the photon excess. The excess and the number of photons.
Well, you need a certain number of Lyman alpha photons for the gas temperature the spin temperature to equal the gas temperature. And you have to find some way to do that. And it could have been an early population of galaxies that did that. So I think that's probably the most likely, but I honestly don't know.
Galaxy structures, which we don't observe.
Yeah, well, we couldn't have observed them because they're too far away and too small. But it's hard. I mean, you'd need a lot of galaxies at that time to produce that. So the EDGES result, if it's correct, I think is quite different from what we were expecting. And, I don't know what it is, to be honest.
It could also be not a systematic, but still in the sky, some kind of a foreground structure that we don't understand or coupling to a systematic. That's also.
Although, again, I mean, you see it in every different.
Yeah, well, if it's.
You mean it's something which is in all parts of the sky?
Yeah, maybe.
It's a mystery, it really is.
Any other questions? Yes?
What would you do with going into space? Because you had a rate of
Not the... But going into space, okay, I didn't mention this, and it was on one of my slides, but the ionosphere is also an issue because the ionosphere, it's like the atmosphere for optical light. It moves around and it creates problems. So the real advantage for doing this, for going to space, is to escape from the effects of the ionosphere. At around 150 megahertz or so, around redshift 7, the ionosphere effects are not that big, and they're expected to be on angular scales, which aren't important for what we're measuring. As we go to the heating era at redshift 20 or so, and certainly as we go to the dark ages, redshift 100, I think the ionosphere is not going to be able to work at redshift of 100. So going to space really allows us to go to the very lower frequencies. Going to space does not solve the problem of the galaxy and other. Going to space does help get us away from radio frequency interference if we go far enough. If we stay in low Earth orbit, I don't think it will help very much. If we can go to the far side of the moon or very far out, then it would be helpful to go to space. The problem with space is cost, of course. So you need a good reason to go. So.
Andrea?
Yeah, Jackie, I think that one of the interesting perspectives about scientific is not only to look for the first stuff, but also, for example, to study the nature of dark matter. And you maybe look at the annihilation signal
Yes.
of dark matter. You need to go to low frequencies before the first stars form. So I see that with Hera, you're planning to go down to 50 megahertz
Yep.
or something. So what do you think of the perspective in terms of that experiment?
Yeah, I'm not sure we're going to be able to actually do cosmology down to 50 for various technical reasons, probably maybe to 60. But yeah, I think we're all, on one of the plots I showed, there is as you well know, if there's dark matter annihilation, it'll inject a lot of energy into the intergalactic medium. And so you'll get a very different history of the temperature of the intergalactic medium as a function of redshift potentially for various dark matter bottles. And we should be able to see that if we can extend to the lower frequencies. It is sort of difficult in the sense that if there's an additional heating, it makes the signal go away, which makes it harder. You don't really know whether it's gone away because it's really gone away or because there's something wrong with your measurement. Yeah, but I think that's an extremely important thing to do in the future, and some of the cosmology, the basic fundamental cosmology can be done at very low frequencies when you don't have to worry about the astrophysics of what's going on. It's just the density enhancements from the initial conditions of inflation or whatever set down the initial conditions. I think that's quite, maybe 10 years in the future, which is why I didn't spend too much time on it at this, but certainly a great potential for this type of measurement.
Any more questions? If there are no further questions, I thank Jackie again.
Well, thank you for your...
And you're welcome to refreshments outside.
Okay.
Nice talk.
Let me turn this off. Yeah, sorry, my tummy got a little bit thrown off because I couldn't see
Technical geometry is great.
Yeah, that's what I had, but this was over on the other side. Yeah.